Good evening. I would like to extend a warm welcome to our speaker, Rahul Mishra, and all the attendees for our event on behalf of the Research Society MIT. Cognizance is an initiative that hopes to bring together people interested in research in various fields. Our organization, our organization is confident that this talk will provide value to everyone attending. Before the presentation begins, I would like to define the structure of our talk today. The chats will be open to discussion for all the attendees throughout the talk. You can put up any questions you have in the chat or raise your hand, and we will be putting them across to the speaker. Our team will be moderating the chats, so we request everyone to keep the contents of the chat related to the topic. Having said that, I would like our moderator, Aditya, to introduce our speaker for the day.
Thank you, Triti. Good evening, sir, and everyone present here. I am Aditya. I would be the moderator for the today's session, and I would like to begin with introducing our speaker, Professor Rahul Mishra. He's currently an assistant professor in the Center for Applied Research in Electronics at IIT Delhi. He was a graduate student at National University of Singapore before obtaining his PhD in Electrical and Computer Engineering. And further, he has also worked as the postdoctoral researcher at National University of Singapore. He did his BTech MTech dual degree in electrical engineering from IIT Kanpur, and he has worked as a component design engineer for Intel. He's a recipient of various national and international level awards and recognitions, some including President's Graduate Fellowship and Academic Excellence Award from IIT Kanpur. He has over 19 published papers in the field of Spintronics and an impressive 690 citations. He has also delivered several talks and presentations in very highly reputed conferences across the globe. So with these few words, I would like Professor Rahul Mishra to begin with his presentation.
Okay, thanks a lot, Aditya and Tirthi, for the warm welcome and for my introduction. And thank you, the Research Society of MIT, for inviting me. And it's my pleasure actually to interact and introduce this subject of Spintronics, especially to the undergrad. Especially, I learned from Aditya that most of the audience consists of the first year. So it's always a pleasure to me if I get to teach this subject to someone who doesn't know much about the field and who has just entered the field of engineering and research as such. Okay, so having said that, maybe I'll share my slide. Okay. So can you see my slides?
Yes, they are visible.
Okay. Okay. So the topic of today's presentation or my talk, it will be on basically on Spintronics, and I'm sure this Spintronics word looks familiar, but I don't think most of you are familiar because it's not a very big field in solid state. Most of you are familiar with terms like microelectronics or solid state, silicon electronics, but Spintronics is something which is still in a very early stage. So not many people are familiar. And about myself, so I'm Rahul Mishra and I'm from IIT Delhi. So although Aditya already introduced me, but I put one slide about my introduction. So I can again, quickly introduce about myself and tell you, specifics about where I work, how I worked, etc. So at present, I am assistant professor in the Center for Applied Research in Electronics. So this is a center in IIT Delhi. So in IIT Delhi, we have departments and we have centers. Okay. So this is one of the center, and center, the thing is we specialize more in research. So we don't have an undergrad course, we have MTech course and we have PhD courses. But the main focus of the centers in IIT Delhi is towards research. So apart from Center for Applied Research in Electronics, there is Center for Biomedical and Center for Energy, etc. And this is the website. So our center, the main focus of our center is working towards developing devices, useful devices basically for various, we work mostly for making devices for defense, organization, things like that. And there are three branches in our center. One is working on this microelectronics, another is working on basically signals, and another is information processing. So if you guys are interested, you can go to this website. And if in the audience there are people doing their MTech or in the final year and want to pursue their PhD in this field, electronics and etc., electrical, then they should definitely check this website out. So I joined recently. Basically, I didn't even finish 1 year. I joined in September 2020. And before that, I did my PhD and postdoc research for some years. Normally, people tend to, after PhD, they go for postdoc somewhere else, some other university. But after finishing my PhD, I continued there for 1 year or something, and then I applied for a professor position. So my PhD was from National University of Singapore, and I was in the department of electrical and computer engineering. And it is there I worked on Spintronics basically. And I worked in the area of Spintronics for basically we use spin devices to make memories. Okay. So right now our memory is made up of silicon. So we want to make spin devices for memories. And my postdoc research was on the same. In postdoc research, I also worked on this new topic where we want to use this spin devices for basically bio-inspired computing, making devices which mimics the human brain. And before that, some years, I worked in Intel as a component design engineer. And in Intel, I worked basically, we had this team working on this server processor, 14 nanometer server processor. So I worked in that team, basically in the design synthesis. And before that, my BTech MTech dual degree, this was from IIT Kanpur, and I was in the electrical engineering department. So, I mean, the key message from this slide I want to give is basically research. The one hard thing about research is it takes some time. If you want to get some real, if you want to do some real research, it takes some time. Basically, starting compared to the age you are right now, right? So it will take some time because PhD and then there is postdoc and maybe you'll do some job. In fact, in other field and outside India, the postdoctoral research can still extend for 3 to 4 years. So you should keep that in mind. But after these many years, 6 to 7 years, you get real fruits of your hard work and all in form of the work you do. Okay. So all the credit for my research right now because I recently started this group in IIT Delhi. So all my work that I'll be presenting today and whatever I've done, the credit goes to my professor, Professor Hunsu Yan. So he is the Global Foundries Chair, Associate Prof. Global Foundry, I hope few of you know, it's one of the biggest foundry in the world right now. And he was also the IEEE Magnetics Distinguished Lecturer. So all credit goes to him for the research. So this was our lab was called Spin and Energy Lab or we called it SCL basically, and it was very fun. All those 4 or 5 years in lab, and this is how our lab looked like. Okay, so if you see this area of Spintronics, in fact, the area of microelectronics is one of the expensive area of research. There are some areas if you are working in computation, if you are like let's say in computer science department or in electrical only, if you are working on some communication etc. Then most of your things can be done on a computer. All you need and maybe you need some data from here and there. But the area of microelectronics, okay, in general, and especially experimental microelectronics, it's a very expensive area. So as you can see in the top photo, okay, let me use my pointer. There's a pointer. Okay. So this top photo, okay, this is a clean room. So clean room is basically a facility where most of the chips you made, all the mobile chips you use in computers and in your mobiles, right? So all the chips are made in this clean room. The property of this clean room is it's like highly pure air is there, and there are various standard of clean room. 1 in 1,000, then there is 1 in 10,000. It just defines 1 in 10,000 million particles, something like that. So higher the purity, then the more good your chip will be. Because these devices we work on, they are like in nanometer. So you can imagine what nanometer is. So your hair is like a micron, right? Micron or 10 micron. So nanometer is even 1 by 10,000 of that. So it's very small. So any small dust particle or anything on that, it can really spoil the device. It can cause short circuit. All your effort will go. So we have to work in very clean environment. Okay. So maybe some of the machines you see, let's say this one, this is a sputtering machine. This is where you deposit some film. And this one you see, this is for etching. Basically, you bombard your film with ions and then you can draw various patterns, various your devices you can draw. And this behind you see, this is an electron beam lithography or an electron microscope. So a very nano pattern because this nano devices, if your device is a nanometer, you cannot see it in an ordinary microscope, right? So you need use electrons. So you have this electron beam machine. So you use that to see the device, and it can also be used for patterning. Okay, so you put a photolithography and then you pattern using this electron beam. So this is a zoom version of that same sputtering machine. So this machine is basically a bombard. You take a metal target, you bombard it with argon ion. and then the metals will come out, and then it will deposit on your wafer. So then you get the film. Okay. So I'm speaking very basic, assuming that everyone is new to this. Okay. So I'm sorry if someone in the audience is already in MTech and familiar with all this. He may find it bit repetitive. And this machine you see, which my friend there in NUS was operating, this is known as physical property measurement system. Okay. So this system can actually apply a magnetic field as high as 9 Tesla. So 9 Tesla is a very high field. Okay. So normally, if you have electromagnet or if you have you can apply field maximum 2 to 3 Tesla. So this 9 Tesla field, can anyone guess how do we get? Okay, so maybe this 9 Tesla field we get using superconducting magnet. Okay, so with what happens in this kind of chamber, we have a superconducting coil. Okay, you have a which is below the 10 Kelvin. The temperature of that superconductor is kept below 10 Kelvin using some combination of helium and all. Okay, it's like a very cool refrigerator that you have at your home. Now, because the superconductor is below its subcritical point, that means what? It will have zero resistance. So you can pass very high current. Once you can pass very high current, you can get very high magnetic field, which is not possible in normal electromagnet. Normal electromagnet, if you pass high current, it will burn because there is too much of heating. In superconductor, in the superconductive state, there is no heating. So you can do this. So you use this magnetic field, and then this device can also go to very low temperature, like 2 Kelvin. So you can assume, right? 2 Kelvin is very low. So you can do all this, explore this beautiful physics of your devices, find property of your devices. Okay, all that. Okay, so rest of the presentation, I have divided broadly into 3 areas. Okay, first we will see Spintronics. What is it? We will directly address what exactly is Spintronics and how it is present in our life. It is present in your life, I may guarantee. You may not know. And what is its journey right now and future? What is there in Spintronics? The second question we will address is why do we need Spintronics? Okay. And finally, we will see one application of Spintronics, that is computing memory. So there are some slides on this. So it's a very brief talk. Okay, so first let's see what is Spintronics, what is it, its journey till now. So modern day electronics, okay, everything you use, for example, the memory you have in your computer, okay, the what is this processor you have in your computer, or the processor you have in your mobile phone, anything, some IoT device you have, you have this Google Chromecast, you have this Alexa, the speaker thing, right, which can speak to you, all those things. So all these devices basically use the property of an electron, which is called as charge. So this is the charge on an electron. So all these devices basically use this property. However, the electron have one more property, okay, and this property is known as spin. And the spin of electron can be plus half and minus half. So if we make devices using the spin of an electron, so this area of electronics is called as spintronics. So in these devices, we are basically using the charge of electrons, okay, for their operation. In the spintronics devices, we will use spin of electron. And classically, you can assume an electron is rotating around its axis. Okay, so it can rotate either clockwise or it can rotate anti-clockwise. Okay, so clockwise will be plus half spin and anti-clockwise will be minus half spin. But I would like to emphasize that this rotation, okay, this is just a classical thing. Reality electrons, they don't spin like this. This is just a way to explain. Okay, so rotation basically give angular momentum and we call it a spin. So this you can assume the property of spin. Assume you have a ball, okay. So there are many features of a ball. A ball, you can say it is shape. Second is the color. So shape of the ball is basically what? The charge you can assume. A round ball, that is the charge. And the color of the ball, you can assume it as a spin. So it's shape of the ball. So similarly, electrons have two property. One is, of course, it has mass. Second, it has charge. Third, it has spin. And spin, it is not a property of electron. Every atom has. Every particle has. For example, light, photon. Photon also have spin, but of course, it is zero spin in photons. There are some particles which have spin like 2, -2, things like that. Okay. So in electronics, if you make devices, right, especially if you make computing devices, how do you store data? You store in form of voltage level, right? For example, high voltage may represent a 1 and low voltage may represent a 0. For example, if you want to write data in your memory, right? So if you want to write 1, you will store a high voltage level. If you want to write 0, you will store a low voltage level. Similarly, in Spintronics, what we can do? So Spintronics, you can assume it is like a magnet. Okay, I forgot to repeat this. So one of the best application of Spintronics is the magnet you see around yourself. Okay, so this magnetism basically comes from spin of the electrons. Okay, so spin of the electrons in some special materials, they align in one particular direction. Okay, they give rise to magnetism, which we can see around us. It's like magnetism is there in almost each and every your earphone, speakers, anything that have magnetism. Okay, coming back to this, for example, in electrons, you can store information like this. In spintronics, you can store information in form of direction of magnet. For example, one can be stored like this. If the north is pointing up, if the south is pointing down, this can be called as 1. And if it is opposite, we can call it a 0. Okay, so bits are stored 1 and 0 like this. In spintronics, we can store bits 1 and 0 like this. Okay, so this is the basic principle of using spintronic devices for computing application. Okay, because for computing and digital application, we need these two levels. Okay, for other application, we don't need these two levels. So this is the oldest application of Spintronics. Basically, I should not call it Spintronics because Spintronics is spin plus, you should have some charge flowing, but I should say it's an oldest application of spin. And spin, as I told earlier, it expresses itself in form of a magnetism in micro objects, bigger objects. Okay, so this is one of the oldest application of spin, which is a Chinese compass, as you can see here. Even the modern day compass you see here, they work using the spin of electron, right? Which is almost invisible, but you see how beautifully it all comes together, the spin of electron, and then all the devices you see around us work using this property. So the idea of spin actually, it came up around 1920s when, the world science was led by mostly the European physicists. So there were these three actually physicists. I don't know how to Unback, is that how I should pronounce, and Gaudsmith and Wolfgang Pauli, of course. They came up with this idea of spin. So they, in this quantum formulation, when people were trying to find this model of electron, okay, using this first Bohr tried with his Bohr model, then it was, I think, further modified by later modified, right? So they were trying to fine tune this model of atom. Okay, then these guys thought, something is missing in this model of electron, and then they introduced this idea of spin. So once they put this idea of spin, all the equation they made, it started making more sense. However, the earliest experiment to identify that, okay, how do we know that spins are present in the atoms? This was done by Stern and Gerlach, two European physicists again. So this experiment was very simple. So one thing they kind of formalized, that spin is a quantum property. What is quantum property? One of the principle of quantum property is it is actually quantized. Quantized means it has discrete level, 1, 2, 3, like that. Okay. So what they took, if you look at the experiment, this is very simple. And this was actually done before these guys formalized. So this was done around 1921. So actually, yeah, around 100 years back. So they took this magnet, okay. What they did, there was non-uniform magnetic field between this. How did they do? They used a flat magnet like this, and this was a bit tapered, okay. So due to this, what happened? There is non-uniform magnetic field. And what is the property actually? If you pass a magnetic dipole, okay, between a non-uniform magnetic field, it will try to apply force on the dipole, and then depending on the orientation of the magnetic dipole, it will either go here. Basically, it is a dot product of this magnetic field and the dipole orientation. Then what these guys did, they took some silver atoms. Okay, now initially they assumed, because they are taking, let's say, 100 of silver atoms, and let's assume they have some magnetic moment, each atom has some spin. So these will be aligned, all random direction. One spin will be like this, one spin will be like this, one spin will be like this, one will be like this. Okay. So once they pass it through this, so if they see, the force will be what? Dot product of this dot this, whatever direction. So according to that, they will have different trajectory. One will go here, one will go here, one will go straight, one will go like this. So this zoom, if we pass the silver atoms, so we should get a pattern like this on the screen. All the silver atoms should distribute like this. If you see the blue one. However, surprisingly, what they found is that half the atom went here and half the atom went here. So what this tells that the spin is a quantized property, that these atoms, right, they do not have spin in like random direction. They have spin only in two particular direction. So if you measure spin of an atom along one direction, you'll get only two values. You'll not get values more than two. You'll either get half or you'll get minus half. That is for electron, but some atoms have, because atomic spin comes from electron. Okay, but just assume. So any atom you take, its spin will not be like 0, 0.1, 0.2. It will be half or minus half, quantized. So this is what they proved using this experiment. And of course, as I mentioned, later these guys formalized. Okay. So spin, the first modern, the modern impact of spintronics in information technology on in our daily life is in form of hard disk drive. Okay, so as you can see in this left photo, okay, in 1956 this photo was taken, and this is a 5 MB storage, okay, 5 megabyte storage using magnetic storage, okay. And can you imagine 5 MB? One song that you download nowadays, it's how much? It's, I think, it's 15 to 20 MB. Some IPL match you watch, how much MBs you stream. So imagine doing all this thing that time, okay. So this is how we started, in 1956. This is 5 MB. And now we are, in our mobiles and all, in actually iPod and all, we have this hard disk drive carrying GBs of data. Our mobiles have like 128 GB, right? And maybe more, 1 terabyte. However, the basic principle of this hard disk has remained the same. Okay. So what happens in a hard disk? This used to be in old computers actually. Now also, I should not call it old, but most of the modern day laptops, they don't have hard disk. They have SSD and all. They are faster. So this is a magnetic disk. In this magnetic disk, if you zoom in, then you can see very small island. Okay, I have not shown the zoom picture, but if you zoom in, you can see small island of magnets. Okay, small magnets. Okay, covered all around this disk, and each magnet will be either aligned, let's say, in this direction or in opposite direction. So this direction will represent 1, opposite direction will represent 0. So that's how data is stored. So 1010 you can write, some magnets will be like this, that is 111000, and that's how you store data in the magnetic disk. That's how it was done here. But that time, these small bits have to be very big. They were, I don't know, maybe few inches big. But now these few inches can be miniaturized to few nanometer. So that's why the technology has remained the same. However, we are able to miniaturize it very small to nanometer, even less. Another part of the hard disk is this hand, you see, right? So if you remember, whenever you run computer and let's say you're running some movie, you hear this sound, right? So that comes because, this hard disk is spinning. So whatever data it wants to read, the hard disk basically spins, and that track basically come under this read arm. So at the end of this arm, at this particular end, okay, there is a very tiny device that is also nanometer big, very tiny device. So that device can actually measure the magnetic field coming out. So if your bit is storing 1, some value of some magnetic field will come out. If your bit is storing 0, then magnetic field will come out in opposite direction. So that thing, this particular device can measure. How exactly it measures, I'll tell you later. Okay. So basically this spinning noise, the track comes under it, and then this track can basically move in this direction. Okay. Once it is along this track, then this translation motion can be provided by this motor. Okay. So that's why hard disk is known as electromechanical device, because there is some mechanical motion, then there is some electrical motion, and that's why hard disk is not very fast, because if you want to write information, it can take some milliseconds and all, right? That's why when computers get old, or in the modern computers, if you buy some iMac and all, right, you will see they mostly consist of the solid state drives. So solid state drive don't contain this mechanical motion and all. Okay, they are basically like memories, the computing memory. So if you avoid the mechanical motion, then your storage, reading and writing can be very fast. So this was done in 1956, and then in 1987 and 88, these two German and French physicists, Alan Grunberg and Albert Pert and Peter Grunberg, sorry, they discovered a phenomena, and this phenomena actually led to the miniaturization of this head. So the miniaturization of this part was possible by fabrication. However, the problem was that this particular thing, the reading head, the scientists or the industries were not able to shrink its size. That was a big challenge. Then later, these guys discovered a phenomena for which they were actually awarded a Nobel Prize in 2007. And this is actually one of the quickest, one of the shortest term in which a Nobel Prize is awarded. Normally, it takes 30 years or 40 years to get a Nobel Prize. For example, Higgs boson, the guy discovered Nobel is the theory he gave, I think, in late 60s, and he got Nobel Prize just few years back when it was experimentally proven. Okay, but these guys, it was one of the quickest, and the reason for this was because the tremendous impact their discovery had on the modern world, actually, which we don't realize. Because modern world, now we take everything for granted, the storage and all in our mobile, we don't even think before downloading anything, but all thanks to these guys. So what these guys discovered is, they discovered simultaneously without each other's help, okay, but are at the same time, so they were lucky. Otherwise, only one would have got the Nobel Prize. Okay. So what they discovered, that saw that if you take two magnetic elements, so magnetic elements mean like there can be iron, cobalt, these are the common magnets, okay. And if you put a spacer in between, spacer can be some insulator or it can be some copper, metal, okay. And if the magnetization of these two elements are along the same direction, okay, so same direction means north of this is here, north of this is here, south is here, south is here. This is case one. Case two is if you put them in opposite direction. Opposite means north is here, south is here, and here north is here, south is here, okay. Then in these two cases, if you measure the resistance, okay, so the resistance value will be very different, and there will be a huge difference. For example, 100%. As an example, let's say in this case, the resistance first of all will be low. In this case, let's say the resistance is 100 ohm. In this case, the resistance will be 200 ohm. So you're not changing the material. Your material is same. You are just switching the magnet. Okay, this magnet you are switching from this to this direction, and the resistance jumps. Basically, it increases. So this was a very simple looking discovery. It's very simple discovery, but it had a tremendous impact because this particular structure, the thing is, it can be miniaturized in nano dimension. So this structure scientists were able to miniaturize, and how this can be used as a read head. So basically, let's assume your hard disk is here. Okay, let's say the hard disk is like this. Now some bit one come. Okay, so one will switch this, so it will go in high resistance state. Then you'll measure. Okay, high resistance. That means you're storing one. Let's say bit zero comes, so zero will switch it back here. Then you will see, oh, it's a low resistance state. So low resistance means you are storing zero, like this. This is how the reader works. Another credit for the whatever we are enjoying right now goes to this guy in Stuart Parkin. He is in IBM. He's still now, I think, is in Germany. And his contribution was basically he gave a very simple and cheap way to deposit this. So how these guys deposited these structure, right? They used a technique called molecular beam epitaxy. So earlier, if you remember, I showed you a photo of what do you called machine. So I operated sputtering machine, and it's actually relatively simple. And you saw the size, right? It was not. It was big. It was like like a master bedroom big. But MB machine, that is a very dedicated technique. It's a very sophisticated, first of all. And the size, you can assume it can be even double the size of that sputter I showed. Okay, and you have to be very careful. There is contamination, and the main problem is the deposition rate in MBE, molecular beam epitaxy. It deposits layer by layer, so the deposition is very slow. Okay, so if you want to, let's say, start a company, if you want to, in your company, if you want to produce this read head, okay, if you want to make hard disk, now if you purchase a MBE, then your deposition will be so slow that you will be able to make like 5 read heads per day. And if you make 5 readers per day, then what will happen? You are making 5 hard disks per day. So you are selling 5 hard disks per day. So of course, but there is demand. People like hard disks. So there is so much demand. So your price will be so high, as we saw that 5 MB hard disk. So the price will be so high, that normal people like us, we cannot afford it. However, if you deposit the same structure by sputtering, which is very fast, then you can deposit maybe 1,000 of readers one day. You can manufacture 1,000 of hard disk drive per day. You can even miniaturize it. Then it will be cheap for everyone. You can sell lots of hard disks. It will be cheap for everyone, and there will be revolution. And this is what happened. And this deposition, this thanks we goes to this guy, Stuart Parkin. Actually, it was assumed, this guy will also get Nobel Prize, but somehow people say that there was some politics and all. This is just a story that runs in the community. But anyway, all three are very well deserving guys. So then the story came from this big data magnetic storage from IBM, which we saw loading in the plane. Then this discovery, and thanks to this discovery, now we have this. We have these huge data centers, uploading the YouTube videos and all. All these things are stored in this magnetic disk like this. Maybe those disks, I think, in data centers are bigger. And these disks are, of course, there in most of the laptops and most of the computers and all these data centers, Google, I mean, whatever you use right now, for your phone, whatever cloud services you are using, Amazon services, and then iPod. So initial iPod used, I don't know if anyone had this initial iPod. This used a very small hard disk drive made by Toshiba. Okay, so it was kind of mechanical. However, nowadays iPhone and most of the phones, they don't use hard disk drive. They use SSD. So not only hard disk drive. Now recently what people are trying, actually one of this is already in market. This is a magnetic memory. So hard disk drive is what? Hard disk drive is more like a permanent storage. Permanent storage, and it's for a long term, right? Let's say you want to write a movie. So you'll put it in your hard disk drive, right? So you can turn off your computer, even after 1 year you can watch. However, when you do some calculation, right, in your computer, or you run some program, or when the movie is playing, so the processor does not interact with the hard disk drive. The processor interacts with the main memory. Okay. If you remember, anyone has opened a computer, and in the initial slide I saw there was a photo of a memory. Okay. Nowadays, I think most of you guys have laptop, right? So you must not have opened a computer. But if you open a computer, there is a flat memory stick there. Okay. It's called a RAM. So that is a main memory. So that memory is the one which interacts with the processor. So processor calculates something. Let's say it's doing two. It has to do 2 plus 5 into 3. So 2 plus 5 it will do, it is 7. Then it will put in the memory. Then that 7 it will take out from the memory. Because this memory, it is not mechanical. It is solid state. Okay. So that's why it can operate very fast. This can operate, not this one, the silicon memory, that can operate in nanoseconds and all. Okay, so that's why the processing is very fast in our computer, right? So the current idea is using in Spintronics is to use that Spintronics in memories. Okay, so now we use semiconductors. So the idea is to use spin elements to do the same thing. How to use? So it's the same principle. Okay, as I mentioned, using the resistance state. In semiconductor, how do you store information? Basically, I mentioned you store pi and 0. In main memory, how it is used? High voltage is 1, low voltage is 0. In Spintronic, how you can use? Using the discovery by the two Nobel laureates, you have this element, basically, and if you have aligned them parallel, then the resistance will be low. So you can store 1. If you align them anti-parallel, resistance will be high. So you can store 1. And recently this STT MRAM was actually commercialized by a company. And some of the smartwatches I heard, like Huawei and all, they consider this spin transfer torque or magnetic MRAM. They don't consist the normal MRAM. So one main advantage, why are we using, right? One advantage is the spintronic memory. If you want to store data, you don't need any electricity. Once the magnet is in this direction, right? Even if you turn off the power supply, it will remain like this for 10 years. However, in main memory, right, the voltage level, right? If you turn off the voltage, what happens? The memory just goes. For example, the MS-DOS document, right? If you are doing something you did not save and your power, there is some power cut, then everything is gone. So that's what happened. However, if you have a spin memory instead of this, then what will happen? The data will not go. So your MS-DOC will not vanish. your whatever file you have written, project report, etc. That will not go anywhere. So that is an advantage. I mean, this is a way to say, but of course you are saving power using that. That's the main advantage. And if you save power, you can use the same power you are providing to do more computation. Okay. Okay, so after giving a brief about the journey of Spintronics, a few slides we will see why exactly we need Spintronics, or actually why people are doing research in microelectronics. Apart from Spintronics, there are other methodology, like 2D electronics. People are working on graphene and other materials. Okay, so we will see. So if you look at the processor frequency over the year, right? So I think the initial processor came around 1971, launched by Intel or something. Okay. So if you see, the speed was like around 1 megahertz. However, after that, continuously there was increase in the frequency. The frequency is basically how many instruction you can process. So higher the frequency of operation in a processor, basically that many instruction you can process. Okay. So if you want to do some calculation, it can do faster. More is the frequency. So if you see, it kept on increasing continuously. So which was very good. Everyone was happy. It's increasing, no problem. Then from 2005, no matter how much they tried, they could not increase the frequency beyond some. There were many problems. The power was increasing. If you increase frequency, what happens? The power consumed or the energy consumed keeps increasing, right? Because you're switching basically phi and 0, phi and 0, phi and 0, plus 1, plus 0, minus 0. So this switching, if you multiply it by frequency, then there is dissipation of heat. So beyond this frequency, basically there's too much power dissipation. So that's why people are not able to increase frequency beyond this. So that is one problem why we need post-silicon technologies beyond the silicon, so that we can keep this frequency increasing, so that we can get more faster. Our YouTube videos can buffer faster, or Facebook post can, you can upload them faster, etc. Another problem is, so all these problems I'm telling, they are basically related to each other. So the technology is scaling. Okay, so what do you mean by technology? So basically all your chips, etc., right? They're made up of small transistor. Okay, so for example, actually we started in micron size, and there was this person Gordon Moore who founded Intel. Okay, he predicted that after every 2 years, basically the size of this your transistor will shrink to half. So if your size is shrinking to half, what you can do in the same area, now you can pack double the transistor. Earlier, let's say you are putting 10,000 transistor, now you can put 20,000 transistor. And more transistor means what? There is more circuit to do more calculations. Okay. Earlier, what would happen? You have to, first do this calculation, then only it will go to next. Now, because the circuit is more complex, just like if you have a bigger brain, you can do more things, right? So circuit is more complex. So now you can do more powerful calculation. So these things, this transistor size as predicted, it kept on shrinking, as you can see. So all this is possible due to many things. I cannot pinpoint. Intel, all these industries, basically they do too much of research work on this. Basically many things. Basically all the deposition thing they have to optimize, and then small patterns they have to make on these devices, which you cannot see with your eyes. So those patterns they have to make. So those lithography techniques have been refined, and then many things have to be refined. Along to all this. However, it was thought, that the power dissipated per area, power density basically, it should remain constant. Okay, because if this power density increases, then basically your chip will start getting heating up, right? It will heat up. Right now, power density, if it remains constant, then your complete chip, let's say it is emitting 5 watt in 1980, and now also in 2000 it is emitting 5 watt. Okay, and in 5 watt it is doing more calculation. So that is like very good. But we saw that that is not exactly what was happening. The power density kept on increasing slowly, especially after 2000. So there was the researchers or people working in industry, they were not able to keep this power density down. And this happened actually because of miniaturization and all that. Because what happens when you miniaturize, your leakage power is when your device is off. That also started contributing a lot. So the power density kept on increasing, and it is because of this increasing power density that frequency has to be, we cannot increase the frequency beyond, so that the total energy doesn't increase much. Okay, So another factor is the processor performance, which I talked earlier. So processor performance, if you see, it's increasing so well here, but after 2000, it has kind of tapered. So this unit, you can, maybe you can assume it is instruction per second or something like that. So it has more or less tapered. So we are not getting much. So that's why, right now, earlier, if you buy one computer in 1990 and by 1995 your friend purchased, then there will be a massive difference. But right now, if you purchase a computer today and 3-4 years down the line, if you purchase again, then there is not so much difference actually. So because of all these things tapering off. Okay. But the problem is in the world, modern world we are living, okay, let me first go through this also. Another is the performance. So the processor performance is increasing, like we showed earlier. However, the memory performance, like how fast your memory is operating, that is not increasing so much. However, your computer system, basically it's a processor and memory together, right? So they both have to work together. However, if they are not working together, one is slow and one is fast, then what the eventual speed will be this only. It won't be this. So the memory is basically becomes slow. So the thing is, our demands are increasing every day. Now, before 5 years, actually, no one in India had internet or mobile and all. Now everyone has mobile, everyone is playing game, PUBG, etc. Everyone, even in villages and all, people are, making videos, watching videos, many other things. And now there is this AI and all, which I'm sure most of you are, interested in working now, and data science, which are like very computing intensive tasks. Okay, so these tasks demand very high computing power, but unfortunately the computing power is kind of saturating. So it's kind of not a very good thing for the for our humanity or for the world or for the industry. So that's why we need this alternate computing things. We need some other devices, some other type of devices which are work on different mechanism. Okay, so that our this progress of our race, I can say, it can continue. We can keep enjoying the things we enjoy, do more progress in medicines, all the kind of progress, more progress in chemistry, all these things we can do if we keep on improving these devices. So that's where Spintronics come. So Spintronics basically tries to fill up some of the gaps in between, some of the weak point of silicon that is Spintronics trying to fill. So if I want to summarize what is happening, why do we need? Because the performance is stagnating, power efficiency is decreasing, processor memory gap is increasing, and then there are some systems like neuromorphic and all. These are advanced systems which people try to make, and the transistors are basically not very optimized for this. So Spintronics, the advantage, what is the advantage? I told earlier, it is non-volatile. The normal silicon is volatile. If you turn off the power, data will go. Spintronics, it is non-volatile. If you have a magnet right at your home, you don't plug it to the charger or something, right? It stays like that. North pole remains north, south pole remains south. So Spintronics is non-volatile. So if the device is not working, then what happens? It consumes very low power. So therefore, we are able to save very much power. And it is also scalable. Scalable means we can shrink it to nanometer dimension or beyond. So if you shrink, then you can package more function you can put. It will be cheap. Everyone can use it, and of course it is fast. So these are the advantages. That's why we work on Spintronics. Okay, so finally, one application of Spintronics actually we already discussed, which is hard disk drive, which already impacted you. But I think most of you know it contains an element of Spintronics in form of the way data is written, and especially the read head. Read head is a Spintronic device. Another application of Spintronics I briefly introduced earlier, which is in form of computing memory. So if you look at the memory pyramid, okay, there are many class of memory. This is the hard disk comes here. Then we have the DRAM. This is the strip which we see in the computer. Then these are the cache memory. So this is there near the processor. Okay, you normally don't see them. And then there are CPU registers and all. So this is called a memory pyramid. Why? Because if you go up, their performance increases. That is, they become faster and faster. These flash drives and all, right, they take microsecond, millisecond to write data. DRAM take tens of nanoseconds, 16 nanoseconds. SRAM take 2-3 nanoseconds. And then the CPU actually it's in 1 nanosecond or less, picosecond actually. However, if you go down, what happens? They become cheaper. That's why. Otherwise, we can use SRAM for data storage also here also. But if you go down, they become cheaper. So magnetic memory, the storage, right? Hard disk is very cheap, so we can use it for storage. So if you go up, the cost also increases, the performance also increases. However, if you go down, it becomes cheaper. So if you see, there are some gaps here, there is some gap in terms of their performance here. There is some gap, in terms of performance here. For example, if you have magnetic storage, magnetic flash drive, in form of a MRAM, then, your computer can become even faster if your long-term storage is made up of magnetic devices, because they are non-volatile, plus they are faster than flash drive. So the unit of the magnetic memory is basically a magnetic tunnel junction. Okay, so this device I already introduced earlier. So this is the device invented by the Nobel laureates. Okay, but they did not invent the magnetic tunnel junction. They used some other layer here instead of. So right now, magnetic tunnel junction consists of insulator. Okay, which is MgO. However, those guys used what? Copper and etc. So insulator, what is the advantage? These guys saw that the difference of the resistance can be very high. It can even go to 200%. If you put copper and all, so those guys saw a difference of only 10 to 20%. Okay, that was enough to get a Nobel Prize, but not enough to use in a magnetic memory. So if you want to use in a magnetic memory, if they found that if you put MgO and all, then the electrons can tunnel basically from one direction to another, and then the difference of resistance will be very high. And higher the difference of resistance means what? It is easier to read, right? So the first generation of MRAM, magnetic RAM, actually came. Okay, maybe go back. So in this unit, basically, one of the layer is fixed. It does not change. And this is the green layer is where you store the data. So if you want to write 1, you align it anti-parallel. If you want to write 0, you align it parallel. So the whole endeavor is how to write this information, how to switch this small magnet, because this magnet is, in nano dimension, micro dimension. So the first approach was what? One of the way to switch magnet is if you put some lines, this metallic lines, and as you know, current carrying wire, what? It produces magnetic field. Then you pass current through this wire, it will produce some magnetic field and it will switch this free layer. So if you want to write 1, you pass current along some direction, it will switch to 1. You pass current along opposite direction, it will switch in different direction, it will switch to 0. However, the disadvantage of this type of memory is what? It is not scalable, as you can see clearly. If you go in nano dimension, it's not able to fabricate this kind of structures which can apply current like this. And again, it is low density. So then people came up with this idea of spin transfer torque MRAM. So the idea is if you pass current through this layer, let's say you pass current here, what they saw, let's say the electrons are coming here, they are unpolarized. That means their spin are aligned in random direction. Once they pass through this layer, they will become polarized. Their spin will be aligned along this direction. And then these electrons, once they go to this layer, okay, which is storing the data, they can switch it. They can transfer their angular momentum to this. So by passing current, you can basically switch this element from one direction to another. And that's how you write data. So now this memory is what? Spin transfer torque memory. It is more scalable. You can shrink it further. And that's why we are able to now put it in some smartwatches like Huawei and all. However, this also has one disadvantage. What is the disadvantage? The endurance is very low because you have to pass very high current, many times. And this MgO layer in between, it is very weak. So if you pass very high current, what will happen? It will break, it will melt. So your memory will not last for a very long time. So it's a cost. And again, for reading also you have to pass current, right? If you want to see if it is storing 1 or 0, right, you will pass current and see if it is a high resistance state or a low resistance state. So that problems are there. So in 2010, it was discovered, right? One way to switch is if you have some materials like heavy metals, okay, and you pass some current, then spin current will be generated. Spin current is basically, one spin going in one direction, opposite spin going in opposite direction, okay. Spin current will be generated and these spin currents can be used to switch the magnet. So what we can do is basically, let's say in this figure, this heavy metal can be placed here. You can pass current here. Then to pass current here, then this element actually here, this is the free layer, right? So you pass current here, then this element can switch. So you don't have to apply a heavy current in this direction, right? So your endurance will automatically increase. So this is the current area of research in the community, basically the spin orbit torque MRAM. And this is basically what I worked on during my PhD and what I'm working on. So this slide is just advertisement. Okay, so don't worry if you don't get many things, because of course if you have a good background then you'll understand. But I'll quickly go through it. So for example, we showed that if you use some other type of material known as ferromagnet, then the efficiency can be very high. You require low current, and if you pass this, you can grow a thicker magnet in this, right? So if you grow thicker magnet, then they will not switch so suddenly. And then I also showed this, you can program these devices, so that they can switch in one direction or another. You can program it basically like a flash drive. So all these things. And if any of you find interesting and all, right, so you can read this detailed review by myself and my professor. It is in IEEE transaction magnetics. So it gives detail. These are some of the areas I introduced which are popular. There are other areas also in which Spintronics are used, like sensors, and it is used for terahertz generation, in flexible electronics, etc., and even for computing. So all these details are there in this paper, and on internet also. If you read, there are videos and all you can watch. So this is almost like the end of my talk. And before ending, I would like to say, so people when they think about research, they think, we'll fly rockets and all this. But this is a very popular cartoon. I saw it long back, and I just searched it on internet and I put it in the PPT. So basically, what is your research? People, if anyone wants to go and research them, you may feel, what am I contributing in research and all? If I do a PhD, if I become a professor, or if you do a research in industry. So basically, this is the all the human knowledge. Assume this is all the human knowledge we have right now. Okay, and this is what you contribute into this as your PhD. Actually, maybe as a professor also, this is what you contribute. Small blip in this whole globe, but this thing will give you happiness. Plus, if each one contribute, then what happens? This circle basically it keeps on increasing, and that's how human knowledge increases. And you can see how we came from nothing, from 2 to 300 years, to where we are. This is all due to the small contribution of research by many scientists, and then work by engineers who then scale these things up. So this is a take-home message for all of you. Okay. So with this, I come to end of my talk. So thank you all, and then any questions or anything, please feel free.
Thank you very much, sir. That was a really interesting presentation. Yeah, the inclusion of pictures of your labs and the equipment that really helped explain the topic. So
So
with
one
that,
thing is like my speaker was off. I just saw, so I don't know if anyone asked question during the presentation. I'm sorry.
no,
Yeah.
like we kept it in the chat, so we'll ask
Okay.
you.
Okay.
So like
Yeah.
if anyone has any questions, they can put it up in the chat and we'll ask them to the speaker. Okay. So GB Raghav Krishna is asking, can we use Spintronics to build quantum computers?
Spintronic to build quantum computing. So I mean, Spintronics, it's a very vague term, what you call Spintronics. But basically, one of the way, so quantum computing basically consists of quantum qubits, right? Qubits are basically right now, if you want to store one, you need one bit, and zero, you need a bit. Qubit basically they can have superposition of two bits together. So one of the way to make qubit is using spin state. Basically, you take some atoms and they have two spin state, right? So superposition of those two spin states are actually used as a qubit. So I don't know if Google or something, their bits are there. I think they are using superconducting bits, which is not a spin qubit. But maybe some company, Microsoft or someone are using spin qubit. I'm not sure. But yeah, spin in this form can be used in quantum computing.
There was another question from Abhishek Rao. He asked, what's the application for Spintronics in industries, and how is it useful, and which industry uses this new technology?
So Spintronics is not only used by industry, it's used by consumer also. Okay. But if you're asking specifically about industry, I mean, it's a computing device. Right now, if you make a memory, right? So same memory is used by you, same memory is used by the industry, right? It's like how asking how industry can use the computers, right? So same computer is used by you, but maybe a more powerful computer can be used by the industry. So that is one way. But other way in which Spintronics are used, Spintronics is also used to make different kind of sensor, for example, the Hall sensor, right, which measures the magnetic field. That is used by almost all the industry. And many actually other sensor are made up of magnetic elements. So that's how industry uses. And industry actually, it's especially heavy industry. They are dependent on sensors, to monitor their equipments, to monitor their products. So that's how Spintronics are used. basically making sensors and actuators and all. Okay.
Uh, there was another question. For a
Yeah.
beginner, what would be the very first steps and learning resources to work eventually in Spintronics at an undergraduate level?
A very first step is, I mean, first it's good to know the background of Spintronics. It's good to have some fundamentals about magnetics and all. So if you are really interested, you guys can just mail me. Then normally to my students, right, who join PhD under me, I forward him one lecture of this Stuart Parkin, which I showed earlier. I forwarded him one lecture of that guy. It's a video who gives a very nice background about Spintronics and all. And then I forward them one book. So if they read their book and all, then that is enough actually to know something about Spintronics, because it's not such a massive field that you have to read 2 3 years. 1 or 2 months if you read, then you will have enough interest in it and you will know what is going on in the community. So that's how I would advise you to start.
Mahendra asks how Spintronics can help in developing low power neuromorphic processors.
Low power neuromorphic processor. Okay, that's a very difficult question. I mean, that's the thing scientists are targeting. Okay, so I mean, first of all, neuromorphic processor itself, we don't know what is a neuromorphic processor. Okay, so neuromorphic field, it's a new field. Basically, it not came recently. Basically, the interest started recently again. It was of interest earlier, but after 20 years, with this data processing increase, now people have become interested in data science and neuromorphic again. So everyone is trying to make up their own definition of this is neuromorphic processor. Some people say, processor that mimics a human brain, that is a neuromorphic processor. Some people say, like the Google GPU, that is also a neuromorphic device. Basically, it does this matrix multiplication and all that. So that definition is not clear. But in terms of how Spintronics can contribute is basically neuromorphic has two elements. Bio like neuromorphic. It is called synapse and it is called neuron. So these are part of the human brain. So actually, in one of my paper, we showed that spintronic devices can basically act like a synapse. Synapse is what? Basically, it can store analog data and things like that. So it's not like a spintronic device can emulate a compute neuromorphic processor, because first of all, we don't know what neuromorphic processor is. But some element of that neuromorphic processor we can give. Okay, spintronic device can act like a synapse. Spintronic device can act like a neuron. And then other people who are working in the other field, they'll try to figure out how to put these things together. Okay.
There was another question. This you kind of addressed by stating the STT MRAMs, but like when can we see Spintronic devices making inroads into consumer hardware?
Yeah, so as I mentioned, it's already there in some of the electronics we see, and companies like Global Foundries, Samsung, then there is Micron. All these are basically they have MRAM division. They are making MRAM, so they are putting basically right now most of the use is it's in automobiles and all, right, because these gets heated up. So people are using in automobile and all, but of course the industries and all they normally don't tell what they are putting in and all that, right? So you, it is already there in consumer electronics. Why I told, but many other companies didn't. Of course, they do not tell because it's like their secret, right? But it is already there in our life, impacting us.
Ang asks, what is the Spintronics equivalent of a clock signal to differentiate between multiple bits?
Spintronic equivalent of a
Clock signal.
clock signal. Basically, you mean a pulse going up and down? Is that
Yeah,
what you?
pulse going up and down.
A spintronic equivalent will be basically your MTJ, right? It is switching from one state to another. That's what I can say. Resistance switching up and down. So your magnet you are switching in two different directions. That can be an spintronic equivalent, I can say. So idea is not to build a complete thing out of only spintronics, because in spintronic MRAM also I told there are transistor basically you need transistors, so you cannot live without silicon. Okay, spintronic is the main storage element, but to access that bit and all, right, you need read transistor and write transistor. Okay, so don't think when I say spintronic devices it will be like complete magnet, no current or anything, no silicon. So it's always a combination of things.
I think if anyone has any other technical questions, they can put it in the chat. We have a off-topic question, sir, if you would like to answer that.
Yeah, sure, sure.
It asks, Ajay asks, his area of interest is robotics, so how should he approach centers of research in IITs and NITs?
Area of interest is robotics. I mean, I think it's good to approach individual faculty. That should be an approach. So you will go through the website of IIT, okay? Then there are various departments and centers. So don't think I can do research only in center. There is no difference in terms of research, okay? So you go to the individual page of website, go to individual department website, then go to some professor's page, okay? Then you see if their area is matching what you like, what you like to do. Then you email them. Then you express your interest, okay? But normally people, what do they write a very half-hearted email? They just say I'm interested, I'm with them. You show your interest properly, you tell them what you have worked on. If you have done something, you can attach a PPT or some document that you've already done this. Like be specific what you want to do. Normally, if you write vague email, most of the time professors ignore it. So be very specific, so that no, you are interested. Be specific in what you are interested in. Then normally people actually come for internship and all. Sometimes it is paid. If you want to do free, I mean, depending on funding the professor has, it can be free internship. But that is a way to start, basically, in summers and all. Many professors are actually quite happy to take interns if you are really interested and if you are able to work. So don't do it for resume. Do it for your knowledge and things like that.
So, I think that's it. If anyone has any other questions, they can raise their hand or put it in the chat. Okay, so I think that's the major part of the questions. Thriti, you can take over. Okay, someone just raised their hand. Okay. So, Siddharth, yeah, you can go ahead. Wait. Yeah, Siddharth, you can go ahead. Hello.
Hello.
Yeah, you can go ahead.
Hello. Am I audible?
Yeah.
Yeah, I was asking that I couldn't understand the working of this MRAM. So can you explain that once again, like how it changes direction and
Okay. So
it affects
maybe,
resistance? Yeah.
okay. Can you see my slide?
Yeah.
Okay. So MRAM, I told the basic element is this MTJ, magnetic tunnel junction. Okay. So MTJ, what is the property? You have two small magnets. Okay. And if these two small magnets are in the same direction, the resistance will be low. If these two magnets are in opposite direction, the resistance will be high. So low resistance can be what? 0. High resistance can be what? 1. So your data, binary data, you are able to store. This thing is clear? Hello, Siddharth?
Yeah. Yeah.
Okay. Now the question is how to switch from one state to another. So basically this one magnet. So the big magnet, we can let it be fixed, and only the top magnet we want to switch. If you want to write 1, we will switch in the opposite direction. If you want to write 0, we will switch it in parallel. So how to switch? So in the current spin transfer torque RAM, the way to switch is you pass a current through this structure like this, up to down or down to up. So these electrons, what happens when they pass through this thick layer? They get the spin of this layer. Okay. Initially their spins are in different direction. Once they pass through this layer, they all align in the direction of this layer. Okay. Then these electrons, they go to this layer and then they transfer their angular momentum. So if this layer was in opposite direction, it will switch again to this direction, to the direction of this. So this is known as transfer of angular momentum from a spin. So one analog is this normal linear momentum. You must have seen, right? Let's say you throw a ball and then one ball is stationary. So what happens? If you throw a ball to a ball of similar size, what happens? If you have elastic collision, right? Then the first ball will stay
Yeah.
there, then the second ball will move away. So the same thing happens here. These electrons are like the balls coming, okay? and this is the stationary ball. So this one will switch, basically move, and the electrons will change in the direction. Okay, so this is the basic mechanism of the STT MRAM.
I understood this one, but I couldn't understand how the different directions of magnetic poles and same directions affects resistance.
Oh, how they affect. Okay. I didn't explain that part. So it all comes down to the scattering, basically. Okay. So what happens when you, okay, assume you pass current, okay, in this direction. So let's assume these two are in parallel state. Okay. Now you pass current in this direction. So the electron will become polarized here. Now what happens if they see a magnet aligned in the same direction? Basically, the density of state. So I'm not sure if you're familiar. The density of state, basically how many empty chairs are there for this electron, will be very high. So these electrons will pass easily. So the resistance will be low. In the second case, let's see this magnet is aligned in opposite direction. Now these electrons are coming here. They are again aligned in this direction of this magnet. Now the density of state, or the number of empty chairs, you can assume, for this side, this side, are less. So there is no space for these electrons to go. No space for electrons to go means more scattering, and more scattering means what? More resistance. So this is how, if you are aligned in opposite direction, the resistance is high. So this is a simple way to understand it. Okay. Basically, it's depending on different scattering of electron, depending on the direction of magnet. If they're in the same direction, then the electron don't scatter much, they pass. If they're in different direction, then the electrons scatter a lot in the second layer, and the resistance increases.
Okay.
Okay.
I had one more question. It was about manipulating spins. So I
Okay.
recently wrote a seminar report on quantum computers, and in that I couldn't understand how the spins of particles are manipulated from up to down and down to up, and from any state to superposition state.
Okay. So I can talk about manipulating spin is very simple. So normally, if you have an iron nail, right? If you have an iron nail, right? If you bring it near a magnet, what happens? It becomes magnetized, right? Then if you take it away, what happens? Sometime if you see it starts attracting other iron nail. I hope you must have done that experiment.
Yeah,
So
yeah.
that's how you manipulate the spin, right? So by how did you manipulate in this case? You applied an external magnetic field. By so you applied an external magnetic field, then the magnetization of all the atoms manipulated in the nail. So this is a simple way to understand it. Same thing we do for small devices, right? What you can do, for example, in this toggle MRAM, that's how they manipulate. You pass current through these wires, so there is magnetic field, and these magnetic field can manipulate the spins. And this is the second way which I explained previously, by passing current, in which the electron transfer the angular momentum. So these are the two ways to manipulate basically a spin, by spin current and by magnetic field. There can be other way also. I mean, I cannot think any other way right now, but these are the two main ways.
But here they are going from distinctly from up state to down state. In the spins in the quantum computers, they went from up to superposition of both up and down, and from down to superposition. So I couldn't understand that part. How
So
did they
that
put in
part even I don't know,
superposition?
because I don't know much about. I
Mhm.
mean, I know the basic about quantum computer, but I don't know exactly how they achieve in it. So even I have to read and tell you that before giving you wrong information. Okay. So I will try to find out. I mean, you can email me so we can discuss later. But right now I don't know answer.
Okay.
Yeah.
Yes, sir. So I think that does it for the questions. Thank you for the talk. I think Triti, you can take over.
Thank you, sir. That was a very interesting talk. I think from covering basics to providing valuable resources, your presentation was also very wholesome. I think we all look forward to more such interactions with you. If the attendees have any further questions on the topic, feel free to approach us after the event and we'll connect you with the speaker. Like I mentioned earlier, we are the Research Society MIT, an organization that aims to connect students and provide resources to promote research. We host a range of events, including webinars, alumni talks, and paper discussions. So do follow us on Instagram and LinkedIn for updates. Even if you are not a part of RSM, you can still approach us with any research interests or project ideas to collaborate with students and professors. Collaborations and projects will be accessed through our website, to which the link will be put up on the chat. We are also open to any suggestions and feedback. So thank you for your participation. Sir, once again, we thank you for today. Have a good evening. Bye.
Okay, thanks a lot. Thank you all.
Thank you, sir.
Yeah, bye.